Okay. So first off, if you earned a low score in project 2, maybe because you did a bunch of work and you failed all the autograder tests, don't worry too much. We're not doing any kind of like, stealth extension-y type thing, but what we'll do instead is sometime tomorrow, I'm going to take a close look at people who didn't finish. I'll get a sense of the distribution. And if there's a clear need, what I've done in the past, whenever we have projects or some people like get 0 points but put in 20 hours, it doesn't feel reflective of what you know. And so I will take some time to set up a process and yeah, basically don't panic. All right. Second announcement is that we're now entering phase 3, the post-spring break phase. We're rounding out the semester. And in this part, we're going to do 2 things. One, we're going to talk about algorithms, mostly sorting, but some other stuff. And then we're also going to talk about software engineering a little more. Well, now, I actually already did one software engineering lecture, but I'm going to do another couple of them. And I mentioned that book that we used for the first lecture. And supporting that idea, there's only one assignment in this phase. I mean, yeah, there's a couple labs, but those labs are also about the project. So the only thing you're going to be working on is this one project called Build Your Own World. You have to have partners for this project, unless you fill out an exception form. It's another chance to do software engineering. And what we mean by that in project 2B, you had to make some choices. And some of them were non-trivial choices, like what variables to use. Like, how many people here created a class called graph? Okay. How many people did not create a class called graph? Like your graph, oh, it's less popular. Interesting. Really? Only that many? There's a lot of ways that you could store your graph. Like how many people used some kind of map to map vertices to their neighbors, like a hash map? How many people used like an array of integers to say who your neighbors were? Okay, some, less hands. But so all these are choices that you make, and the choices you make have a profound impact on how hard it is to do anything. So in project 3, it's that, where you still have to pick data structures, but you also have to decide what classes to decide. So like graph or not graph is kind of a small choice. In project 3, you'll have way more flexibility to decide what classes you're actually going to write, because they're just going to give you a high level spec. First phase is build a world generator. Second phase is make it possible to walk around in the world. Okay, that's more or less the spec. I mean, there's more details than that, but there's not like a specific API so much. It's a little bit, but it's not as tightly constrained as everything else in this class. And just like before, your choices are going to make a huge difference in how efficient your code is and how easy it is to write. Okay, so that's phase 3. Now the lecture part of this class, the speed and the density is lower than earlier. We still talk about cool ideas, but the sorting stuff is not like as quite, brain bending as some of the earlier stuff. Some of it's very beautiful, like quicksort, that's amazing. But I'd say that the class at this point is going to be a little less work. Maybe other classes are a little more. So I'm hoping that you have a little bit of breathing room now that we've cleared the major hurdle of project 2B. Okay. Any questions about all that? All right, cool. So let's talk about our first new topic of, let's fix the year. See, I fixed it in the title here. Okay, just a sense of where I am right now in life. So we're going to talk about sorting. And I'm going to start by first defining sorting. And before I do that, I want to tell you why sorting is useful. Okay, so sorting is going to be maybe like 5 or 6 lectures worth of discussion. And informally, the idea is we're going to take some items and put them in order, but I'll give a more formal definition soon. Now, this is useful, obviously, in real life. Like we sort things, like Google Sheets, sort the sheet or whatever. It's also useful as a subtask. So for example, if I want to say, are there any duplicates in a list? One way to do it is sort the list and then only look at adjacents. That was one of the first algorithms we saw in the asymptotics lectures. If you have items in increasing order, you could do binary search. If you have items that are sorted, you can turn them into, for example, binary search trees that are perfectly balanced. If you want that for some reason, like a perfectly balanced, or other more exotic data structures we haven't talked about, like the KD tree. The other thing that I think is nice about sorting is, in addition to being a thing that is useful, it's also just, there's a lot of cool case studies about how one approaches computational problems. There's a million ways to do project 3. There's a million ways to sort. This is an important part about problem solving in general. There's like really clever ideas, and sorting is a very simple problem with a million cool approaches. And some of those solutions use data structures, which is also nice, this being a data structures class. So the first thing I'm going to do is I'm going to give you a definition of sorting. I took this from, this is probably the most definitive, if you're ever curious, like I want to find the best reference for like quicksort or whatever, like some really famous thing, or bubble sort or whatever. The Art of Computer Programming by Donald Knuth. is a very interesting, very old series of books that this guy's been working on for decades. And he has a lot of really cool historical anecdotes. He talks about where the idea was formed. If you want to know like who in the 30s was thinking about things before there were like easy computers, this is the book that has them. So I recommend it. It's kind of a reference book more than a fun read, but it's a very good book that you should know about. That it's a very great book. Like when I want to go back and find the best reference for something, that's where I go. And so the first thing I'll give you is that he defines an ordering relation in the context of sorting for 3 keys as follows. So we have a less than symbol, and it follows 2 rules. The first is the law of trichotomy. It is either the case that A is less than B is less than A, or A is equal to B. Okay. And then we also have the law of transitivity, which is that if A is less than B and B is less than C, then A is less than C. And an ordering relation that has those properties is a total order. And so then what is a sort? Okay, this seems like maybe a little excessive, but we're putting it down on paper. We know basically what we mean by less than. And so a sort is permutation, which is taking a sequence of items and rearranging them in a non-decreasing order relative to a given ordering relation, like x1 is less than or equal to x2, less than or equal to x3, and so forth. And here less than or equal to means that one of these 2 conditions is true. Okay, all right. So maybe an example of an ordering relation would be the length of strings. So it's definitely the case that 2 strings have either lengths that are equal to each other, less than or greater than. Sorry, actually I'm only using the less than symbol. It could be A is less than B, A is equal to B, or B is less than A. And of course, string length is transitive under this relation. And so there's 2 valid sorts for this array I've given you. Cows get going the. Why are there 2 valid sorts just at a glance? There's 2 strings that have the same length. Okay. So under this relation that we're defining here, V is considered equal to get, like under the ordering relation, right? And so this is an interesting but very small distinction. And it's also true in Java that sometimes the compare to method doesn't have the same semantics as equal. Okay. It may be the case that 2 things, in this case, these are 2 things that might compare to and return 0, but they wouldn't be considered dot equals. All right. So a relation in this sense refers to in the Java context something like the compare to method in Java. I don't want to belabor this too much. It's just want to give us a firm footing, but I don't want to get bogged down in the details because I want to get to the algorithms. So as I said out loud, compare to and equals, they map to, the idea of a relation maps to roughly something like a compare to or a compare method. So for example, if I create a comparator that compares 2 strings by their length, this is the relation right here. This is defining that relation. Okay. Oh. And with respect to this order, when I say V equals get, if I'm using Donald Knuth's notation, it's not the same thing as equals. Small point, and really I just want you to be like thinking about it on the edge of your consciousness, but it's not super important. Okay. But this gives you a solid footing in the same way that sigma algebras give you a solid footing whenever you're learning about probability, but are not absolutely essential to understand the lecture. This idea, on the other hand, is something I really do want you to sink your teeth into because I think it's extremely valuable. And this is something known as an inversion. So an inversion is a pair of elements, if you have a sequence, and it's a pair of elements that are out of sort with respect to some relation, as we defined earlier. So for example, if I look, let me tell you why this idea is valuable. So is this array sorted? No, but is it like kind of sorted? Yeah, right. So it's capturing that notion that's a little bit sorted, right? Like it seems kind of sorted-ish. So what we could do is consider every possible pairing, like 0 and 1, those are great. 0 and 1, those are great. 8 and 6, those are bad. And so I can enumerate every single pairing that is not valid. And if you count up the number of possible pairs, just every, all the pairs, there's 55 of them and 6 of them are wrong. So on the grand scheme of things, where the least sorted array would be in reverse order, 9, 8, 7, 6, etc. And the most sorted array, 0, 1, 1, 2, 3, 4, 5, etc. This one is much closer to sorted. Right? It's only got 6 of the inversions out of 55 max. What ordering of this array do you think would have 55 inversions? Yeah.
If it was sorted backwards.
Yeah, it was sorted backwards. You saw that question coming. You're like, hand up before you finish. You'd be good on Jeopardy. I like that. All right. So this idea, you could aspire it to perhaps Yoda, but the actual inventor is Gabriel Kramer, also known for Kramer's rule, which you might have seen if you took a linear algebra class or maybe a 16 series class. This idea of an inversion, we still use today. Thank you, Gabriel Kramer, or Yoda, whoever it was, I don't know. So another way to state the goal of sorting is to take a sequence and rearrange it so that you end up with 0 inversions. And what we'll see is that some sorting algorithms, they start with the number of inversions, and they chip away at the problem, like I'm always going to take away inversions, it's going to monotonically decrease. And other sorting algorithms are weird. They start with some number of inversions, and it might actually increase and then go back down. And in fact, the best and fastest sorting algorithm does that, which we'll talk about later. Like, it doesn't make things strictly better. It makes things worse for a little while and then makes them better. Kind of like, if you're really good at I don't know, Rubik's Cube, you probably feel less bad about breaking the order in order to get there faster. Questions about this? All right. So I'm going to recall the 2 main definitions from our asymptotics lectures that we're going to use to evaluate the quality of a sorting algorithm, not from its aesthetic. I mean, I will talk about the aesthetics, but one of the key questions is how good is it at its job in terms of using computational resources. And so the first such characterization is the time complexity, like how long it takes the algorithm to run. So like Dijkstra's had time complexity E log V. I'll use big O notation to be a little lazy. We can also use big thetas throughout, but here I've used big O. And we can also characterize how much memory a sorting algorithm uses. So some of them use no additional memory, and some of them might make, for example, an entire copy of the array again and like do some work on that. And so that's the space complexity of an algorithm. So for example, Dijkstra's had space complexity theta V, and that's because it had to make 3 arrays, one for the Q, or sorry, it had to make 2 arrays, one for the distance 2 array, one for the edge 2 array, and it had a Q that could get as big as containing all the vertices. Or if you did it in I think the version that Justin taught, you started with all the vertices in a priority queue where they all started with infinite distance, right? So it take V space. Now, I do want to note that you don't count the space of the array before you start sorting, because otherwise all sorting algorithms have time complexity, or sorry, space complexity theta n. We're only going to be keeping track of how much extra space they use. So for example, Dijkstra's uses only a theta V space, even though, yes, the graph, you have to store the edges. Okay. Just a reminder of what time and space complexity are, because we're going to be using this again a lot. Okay. All right, so all that said, let's jump in and talk about our first new sorting algorithm of the day, Heapsort. That's going to be an optimization of what you've already seen, selection sort. So what's selection sort again? I got to remind you of this from lecture roughly 6, and we did testing. So selection sort we already saw, and I'm just going to do a little demo because I don't expect you to remember it, which is that when we selection sort an array, we look at the array and we say, what's the smallest item? So what's the smallest item? 2. So where should we put it? At the front. Okay. So I'm going to take that and swap it to the front. That's the usual thing we do. We don't scoot everything over. We swap into place. Okay. Now that process, it turns out, not 100% totally obvious, actually, that it will always decrease the number of inversions. So selection sort is an algorithm that always makes things strictly better. It's a monotonically improving algorithm, so to speak. Okay. Next up comes 15. All right. 15 is the smallest thing. What do we do? Nothing. All right. What's the next smallest item? 17. Okay, good. Oops, I skipped a step. Sorry. 17 is the next smallest. We swap. Okay, who's the next smallest? 17 again. Which 17? Depends on how you implement it, but typically it's going to be the first one, just the way people would write the code. So we take this 17 and we swap at the front. But the person at the front is correct in saying that 17 will doesn't really matter which one you do. They'll still be correct in the end. Okay, we repeat this process over and over. And there's another word I mentioned here, which was I don't say it on this slide, but sometimes we use the term fix. We fix the item once it's in place, meaning it can no longer change. All right, any questions about selection sort? Yeah. Right. So the question was, is this a for loop that goes over the entire array? Yes. And that's exactly why selection sort's slow. It's because it's looking over the entire array, looking over the entire array, looking over the entire array. So it feels like there's some inefficiency there. Right. Great observation. And that's the insight as to why maybe we could do better. So because it is a repeated process of looking over the whole array over and over, oopsie, it is going to take n squared time. You do n, then n minus 1, then n minus 2, then n minus 3, and so forth. That's n squared. All right. So Heapsort says, let's use a data structure to make things better, right? Like instead of looking at the entire array every time to find the smallest item, what if we use a heap, which we know is really good at finding minimums of things? So one way to do it is to take all the items and put them in a min heap somehow. But I'm going to say a little weird. I'm actually going to use a max heap, not a min heap. Okay, why? That's a good, what? Okay, so a min heap would work. And this next thing I would do would work perfectly fine with a min heap, but a max heap will let us do one extra trick on top at the end. Okay, so here's the idea. If I wanted to heap sort, again, I could use a min heap for this, but I'm going to use a max. Okay, just to start expanding your mind a little. I'm going to take all my items and I'm going to put them in a max heap. Okay, so here's my input array. I'm going to put them in a max heap and then I'm going to throw away my input array. So if I do that, how do we insert things into a max heap? Well, after I'm done, if I'm using my old heap implementation, I'll end up with this array. I'm not doing all the steps because that was from the priority queue lecture, but let's look at the structure of this thing. Okay, we got 0. Why is this 0? There's a hint on the slide. You might not remember this, yeah? Yeah, like the formulas are a little nicer for left and right and parent. So the Princeton implementation is to leave this blank. So I also did that, okay? Just made the functions nicer for the implementation. Tree representation, I think we called it 3B. Okay, why is 41 here? Because it's the max, right? It's at the top of the heap. In fact, this diagram on the right is what compared to this array? It's like the interpretation of it, right? The 0 is nowhere, 41 is the root, 19 is the left child, 32 is the right child, 17 is the left child of 19, and so forth. Okay? All from that lecture. So if you don't remember all the details, that's fine, but that's what this is. Is this right here a max heap? Looks good. Looks like I did it right when I made the slide some time ago. Okay. So hopefully you agree with me that it is possible to do this. It would just be a little tedious to go through all the steps. Okay. Any questions? So is this array sorted? No, it's terrible. In fact, if anything, it's counterproductive because the biggest item's at the front. Like it feels like we've done something bad, but we can use it now to make a sorted array pretty quick. Okay. So quick question, just that first step before we get to the next part. How long does it take to actually do this? What do you think? You can give me a big O. Be a little lazy. So you got to insert in things. And what's the runtime in the worst case in big O notation for each insert? Log n. Now you might say, well, the first one only took 1, the second one took, log 2, and then log 3, log 4. But I'm just going to upper bound it and say, you agree with me, I hope, that none of the inserts take more than log n time. Like a big O log n, and then I'll just say n times that is big O n log n. Okay, so it's n log n to do this step. Okay. If you wanted a tighter bound, you could say, what's the sum of log 1 plus log 2 plus log 3? I'll let you think about that if you want, but it's also n log n. Okay. So here, when I do deletion, okay, the next stage is going to be what's sometimes called sort down or heap delete, which is I'm going to take this array and I'm just going to call delete max over and over. And every time I do delete max, I'm going to stick the item at the end of the array. Okay. So when I do 41, someone another Zoom meeting? Oh, no. Okay. You're in this one. All right. I thought for a second someone joined another meeting. I was recording that one. Okay. I forgot when you join a Zoom meeting at Warren's being watched. All right. Anyway, where was I? So when I delete 41, and I put it at the end of this array, what's going to happen next when this 41 goes away? Anybody know who's going to be the new root? 32 sounds good to me. Yeah. So 17 is going to get swapped into place. Then we're going to either sync left or right. 32 comes up. Okay. So you end up with this array. Now, again, I don't expect you to be able to do this in your head. When I delete 41, this is the new heap. Okay. And then what I'm going to do is what happens to 41 whenever it gets taken out of the tree? I put it at the end of separate array, the output array. Okay. So the next thing that happens is I know that after that delete operation, the new biggest item here is 32. So when I delete this, who's going to be the new root of this heap? 26. And where's 32 going to go? Right here. All right, so 32 gets deleted and ends up here, and 26 is the new root. And again, it's not obvious exactly why it becomes this exact array. I mean, you can work out the details, but the important part, the part I expect you to be able to follow, is that 26 ends up as the new top. Okay. Right. Next up comes 26, which gets moved there, and so forth. So we keep doing the following. Yeah. Now you can do this later if you want to feel each step out. But the basic idea is, again, I have my array where the biggest item's on the top, and every time I do a delete, the biggest item's always going to end up on top. Okay, that's the big picture. So I think my question about runtime next is on the next slide here in my original. Okay. So actually, before I ask you this question though, any questions about why this works? Yeah.
You alluded earlier that you feel max heap was allow you to.
Oh, max heap. I haven't gotten you to why max heaps are cooler yet. We'll save that. Yeah. But if you did min heap, what would you do? Every time you delete it, where would you put it in the other array? In the front spot. Yeah. Cool. Okay, so what do you think is the runtime of this sort? Which I thought I deleted this. It's not valid. So what do you think is the runtime to do this type of heap sort, which are called naive heap sort? So I told you we already figured out the time to do the first step, insert all items in a max heap. What was the runtime for this? In log n, right? Okay, now you got to think about the runtime for that second step, and I'll just walk over here to Justin and say hi for a minute. All right, I'll take some thoughts. What do you think? How long does it take to do each delete operation? Log n, great. And how many things do you have to delete? N of them. So you have an n log n step followed by an n log n step. So it's n log n. Okay, that's the approach. Good. Okay. So the basic operation or the basic idea here is getting items into the heaps n log n time, finding the largest item, theta 1, removing the largest item as log n for each removal. So you're going to do each of these things n times. Overall, we get big O of n log n. Interesting question. Why did I say theta here at O? I don't have a good answer to that. So I have to think about that one. I know this is off the top of my head, almost, but I don't want to go there right now. I'm gonna think about it and I'll say something at the beginning of the next lecture, but I don't want, like, if you're a little nervous, I said theta here and big O, good for you, but I don't want to go there at the moment. I'm a little worried of my current state. I won't be able to give you a good answer. All right. Memory usage, by contrast, is theta n. Okay. I didn't ask you that. But the reason we have to do theta n is because we had an array, the input array. And then we had another array, which was the heap version with a 0 at the front. And then we actually had a third array, which was the output array. Okay. So ultimately, you're spending like 2n extra memory. You can be a little clever and turn that into n. But what I'm going to show you is I can get rid of all of the extra memory cost with some very fancy trickery. Okay. Let me tell you about an alternate version of Heapsort called in-place Heapsort. So in this alternate approach, we're not going to create a separate array to be the heap. We're going to use the original array to be the heap. You're going to do an in-place heaping. Okay. So rather than inserting into a new array where the front item is 0, and then you got a bunch of other stuff, we're going to use a process called bottom-up heapification, which converts the array into a heap in place. Okay. Now, I'm just going to state this algorithm without proof. Well, I'll do a constructive proof, I guess. It's mostly a proof. I'm going to take my my array and I'm going to sync the nodes in reverse level order. And if you do that, when you're done, you're guaranteed to get a heap. And that avoids the need to make another copy. And then the algorithm will be very similar to naive heap sort with one little trick. Okay. So basically, the idea that I want to show you is I'm going to run a process that I've just said exists called heapification that takes this array and turns it into the heap version of the same without an extra array. So let's see how it works. All right. So what I'm going to do is to do this bottom-up heapification process, I'm going to take each node and I'm going to sync it in reverse level order. So what's the last item in level order? 17. So it's the lowest level, the bottom right. And then I'm going to sync 17, then 41, then 26, then 19, then 7, then 2, then 15, and 32. Okay. So this thing you'll note is not a heap. It's not a max heap because of the fact that 41 is not at the top. Okay, so let's start by syncing 17. What happens when I call sync 17? Nothing. There's nowhere to go. Then I sync 17, then I sync 41, then I sync 26, then I sync 19. Okay. All of those sync operations are meaningless. Some versions of this algorithm say only sync items that have at least one child, but I'm being extra lazy and saying sync even those. Okay. Now, what I can tell you is that each of these, we think of a heap as a recursive data structure. These are each the root of a heap. We know that. Okay. They're just like trivially so. They're just one item. Okay. So now comes the next one that's interesting, which is 17. In this case, 17 has no effect. And after I'm done syncing, because I know that the left subtree is a heap and the right subtree is a heap, and further that I've taken the current item and sunk it, like it could be that this was 6, then it will go down and find its appropriate place. Or it could be that it's 17 or 19 and nothing happens. But in either of those two cases, post-heapification, or sorry, post-syncing, this right here would be the root of a heap. Okay. So right here, this is the root of this blue heap, so to speak. Okay. Now, technically, these two are also roots of a heap, but I'm graying those out because it's kind of like a subordinate fact. These are still true. I just don't care about them. Okay. The subtle argument. All right, let's talk about 2 next. Okay. 2, by contrast, does do something. So on the left, we have 26 and 41. And even if these were, giant trees with thousands of items in them, if they're both heaps and you put 2 at the top, after you sync it, the resulting data structure will be a heap. In fact, that was the property we relied on to understand priority queue deletion. So in other words, if you take a heap and you delete the root and you pick the last item and put it at the root and then sync, we know that that works, right? That's the same basic idea here. If your left subtree is a heap and your right subtree is a heap, you can put any value, 1,000,000, 0, 365, -44, and you do sync, and the thing you get after is always a heap. Okay. So if after I sync, I'm guaranteed that this thing rooted here is going to be a heap. In this case, who's going to take over? 41, it's max heap. Okay. In that case, we can think of 41 as the root of this pink heap. Okay. All right, who syncs next? It's a good question. So we've actually been syncing in reverse level order. 17, 17, 2, 26, 19, 70, 41. So next is, you're right, 15. When we sync 15, does it go down? That's a max heap. Yeah, and who's going to take over? 19. So the next sync is going to be 15 syncing. I don't know why that's missing. So 19 takes over, and now I'll call this the blue side. Lastly, you have 32. So now, do you agree that both of these two halves are a heap? Okay, great. Is the whole thing a heap? No, 32 is in the wrong place. But how can we fix it? We tell 32 to go find its place below. And we know just by, we're guaranteed that either this or this is going to be the new root, right? Because this is the biggest item in the right subtree. This is the biggest item in the left subtree. So we know that absolutely 100% always the biggest item is going to end up at the top. That's either going to come as the blue item or the red item. In this case, it's the red one. And we end up with one big old heap. Okay. All right. And so the basic idea is here, since the tree rooted at position 0 is a heap, the entire thing is a heap. It's a cool algorithm. Now, there's 3 other algorithms you might consider. What happens if I sync all the items in level order? Or what happens if I swim all the items in reverse level order, or swim all the items in level order? Turns out, by the way, that out of those 4 permutations, 2 of those algorithms work, 2 of them don't. And of the 2 algorithms that work, one of them is more efficient, interestingly. One of them takes n time and the other one takes n log n time. This one takes only n time. Okay. I'm not going to talk about it in class today, but be aware that that's the case. Okay, go ahead.
32 is 25.
What if 32 was 25? So at what step? Right. Oh, so if it was 25, then 41 would come up, and that would be good. Then 25 would sync again, because the sync operation is always recursively redone until you're done. Right. Okay, so good point. So if this number had been some other thing, like 1 right? It's going to sink all the way down. Yeah, good point. All right, great. Okay, so if I lost you a little bit because I was being a little too focused on proving you that it works rather than the mechanisms, the important part was this. There is an array. I can turn it into a heap with this syncing process. And I have 100% faith that if you didn't totally digest it, just going through that demo again, you'll be able to do the mechanics of this quite readily. Okay. So after I've heapified, here's the next step. Okay. So hopefully you agree with me that I've taken an array and turned it into a heap without creating an auxiliary array. And so the next step is very clever. So we could create another output array and do the exact same thing from before. But instead, what I'm going to do is when I delete 41, what do you think I should do with it? Yes, that's the exact right idea. So I'm going to take 41 and then I'm going to send it to the back when I delete. So instead of sticking it in some other array, I'm just going to take each item and stick it into the second to last position. Okay, it's quite pretty. So I'd like you just to think about this. If you could do this step, then you understand Heapsort. I'll give you guys a full minute to try and get to the actual answer. All little fiddly bits. Go. To give you a hint, 26 is going to end up right here. Okay. I don't know if you got that, but if you didn't, come back to it later. Okay. So from here on, everything's just the same. So we're done. All right. That's Heapsort. Quite clever. I like it. It's pretty. Okay. Question for you. I already kind of spoiled this one. But what's the overall runtime? The second two steps are the same as naive Heapsort. What do you think is the runtime to do bottom-up heapification? I don't know, I already kind of spoiled this one. So in-log-in is a safe bet. But you can actually show that it is also, yeah, you can also show it's big O of n, way beyond the scope of what I want to do in lecture. But hopefully you feel comfortable saying that it's no worse than in-log-n. And with a lot of cleverness, you can realize it's actually only n. It's pretty fast. Okay. What's the overall runtime of Heapsort? Well, it's going to be even if you take into account the fact that this bottom-up heapification process is n, it's still n log n overall, because that first step of turning it into a heap's n, but then deleting all the items individually is n log. What's the memory complexity of this Heapsort that I've described? Yeah, it uses no extra memory other than maybe some variables. Oh, sorry, I'm going to delete this because it's not important. Yeah, it doesn't use any extra memory other than whatever variables you make, but there's no extra arrays. So it's constant or constant memory. Okay, that's Heapsort. So what I got here, yeah, go ahead.
A little note at the bottom of that slide that shows the difference between the things that are log n data constant and effectively nothing.
Right.
Could you elaborate on that?
Sure. Okay. You saw I had tried to hide it, but the idea is that when you write a recursive algorithm that actually makes recursive calls, you have to use stack space to keep track of where you were. So technically, any recursive algorithm is going to use log n space to keep track of the call stack. But if you have an array of, say, 1 billion items, it just really doesn't cost you much memory. So it's kind of an implementation detail. So even though I was like a little dishonest in saying it's constant time because I wasn't taking into account the stack space, in practice, it doesn't really matter, even if you implement it recursively. Yeah. Fair. Yeah, go ahead. Right. Both of the heap sorts are, in fact, theta and log n. Yeah. Yep. So sorts so far, we got selection sort from earlier, which was an n squared in the worst case. We have Heapsort, which is in log n, and they both use constant space. Heapsort is very fast. Now I want to note this is kind of interesting. You take an array that's originally maybe, in any amount of order, and then you actually bring the biggest item to the front, in effect, like breaking things, and then deleting everything back out. That turns out to be more efficient. To turn it into a heap, which is a little bit kind of backwards from what you want. It's a max heap. Just like that level of order and then deleting stuff out, you end up with a nice, beautiful, fast sort that's in log n. You can also show that the best case is n. We didn't show it, but the case for that, in case you're curious, is all the items are duplicates. That just turns out to be very fast with Heapsort. Now, Heapsort, as it turns out, even though it is an n log n algorithm, which is far, far better than selection sort, it is not very used in practice. In 61C, you'll learn how caching works, but the idea is that Heapsort involves looking at different parts of an array in memory that are very far apart from each other, which just doesn't play well with modern computers. Yeah, so just a note. Okay. Let's talk about Mergesort briefly. Oh, yeah, sorry. Right, so why do we use a max heap as a min heap? Yes, I didn't really make that clear. So if we used a min heap, then we wouldn't have been able to use that nice trick where we take the item and when you delete it, you put it at the end. Yeah. And if you think about it, well, like, couldn't I just keep it at the beginning? It doesn't work because you have to slide everything over. Yeah. Yep. It's an ugly asymmetry. I'm still a little uncomfortable with it. I don't like that it's the case. It feels like it shouldn't be the case, but a max heap really does use less space. You could get around this by changing the semantics of a heap so that you store the heap from the back to the front. Then you could do it. That's how you fix that asymmetry. So, yeah. So I guess you could use a min heap but stored backwards. That would also work. Yeah. Yeah. Or a min heap. Min heap. Yeah. A min heap that stores backward is different than a max heap. All right. Let's talk about merge sort. So we've seen merge sort before, just like selection sort. And I just want to remind you of what this sort was, while we're covering all our sorts. So this is sometimes called top-down merge sort. I won't teach you bottom-up merge sort, but be aware that it exists. But in top-down merge sort, the idea is you first take your problem and you split it in half into a left and a right half. Then you merge sort each half. So when I merge sort the left, what will happen? What's going to be the output? Well, I'm not going to show all the steps. I'm just going to say, what does this turn into when I finish merge sorting it? 2, 5, 17, 32, right? There you go. Okay, so I sort both halves separately, and I'm not showing those steps because it's a recursive algorithm. And then what I'm gonna do is merge these back in. Okay, so I just each of the two halves got separately sorted by some black box algorithm. It happens to be, by the way, the algorithm we're doing. And then we're gonna merge them together. So how do we do the merge step? Well, the idea is we have these two arrays and we say, of the leftmost items, which one's smaller? So which one's smaller? 2. So we copy that one over. All right, 15 and 17, which one's smaller? 15, good. Or which one's smaller, 17 and 17? 17, we'll take the left one. Okay, 32 and 17? 17, 17, 19, okay, 26. What happens next? 32. And at this point, we have nothing left. So we're gonna just copy all the remaining items, in this case on the blue side. Okay, that's merge sort. We already talked about this algorithm a lot, but reminder if that's what it is. Any questions about this one? Okay. So this is another n log n algorithm. And we already talked about its runtime in the past. We said it was n log n runtime. It was actually one of our very first algorithms we ever analyzed. And then space complexity, if you use a copy, like an auxiliary array, in order to implement it, and we didn't really get into implementation details, but if you imagine that every time you make a copy that you're going to copy everything over like we just did, it takes in memory. Okay. You might say, is there some clever trick we could do like Heapsort where we do it in place? Yes, but it is very inefficient and I don't understand it. I've tried reading it a few times. I haven't really given it serious, I want to sit down with this thing for an hour, but it's complicated to merge in place. All right. Anyway. Someday I'll do it. It just hasn't been worth my time, right? Anyway, so this approach, merge sort, is faster than heap sort in basically all cases. So almost never do you actually use heap sort. Heap sort I think of as primarily a mathematical object. It's interesting. It's beautiful. It's a cool way to optimize selection sort. Make it faster by using a data structure. But mostly it's an intellectual exercise. There's probably some little limited number of places where it's actually faster, but I know of no such actual applications. All right. So now let's talk about insertions. Okay. So insertion sort is interesting because it is worse than merge sort. I'll tell you that, spoiler. Yet it is very useful in practice. So let me give you a sense of what insertion sort is all about, tell you what the algorithm is, and we won't really be able to puzzle through all the runtime analysis today or why it's good. But I'm going to get you through one more sorting algorithm. Okay. So with insertion sort, this is the lazy version to show it. I'm going to show a nicer version in a moment that's in place. But with insertion sort, we're going to start with an input array, and then we're going to do go ahead.
So for these algorithms where you're editing an array, they have to be recursive because you can do it iteratively once you hit a very complicated exception.
So if you were to try and do them you could do them non-recursively. I think what you're talking about is if you try to like parallelize them.
Well, but if I start like
Right. So you would not want to run multiple threads with merge sort without being very careful, but you could implement it non-recursively. So any recursive algorithm can be implemented iteratively if you're very clever. There's a way to use actually the stack data structure to take any recursive code and turn it into an iterative implementation. Someday you might write such code, not in this class. Yeah. Anyway. Okay, so this is insertion sort. So the idea is I am going to run the demo. It's my goal. But I want it full screeny. Okay, I guess we're not. Okay, that's fine. We don't need all the pixels. Nope. Okay. All right. So what we're going to do is we're going to start from an empty output sequence, and then we're going to add each item to the output in the appropriate place. That's the naive version. So 32, when I add it, it just goes in there. That's like, it's too confused. It's too simple to understand. When I insert 15, where should I put it? To the left of 32. Where did I put it where do I insert the 2? To the left. Where does 17 go? To the right of 15. 19 goes to the right of 17. 26 goes in the middle. 41 goes at the end. 17, 17. Okay, that's insertion sort. Now this version of insertion sort is really inefficient because you're constantly moving things around in an array. In fact, the version I showed is really weird because I guess you would be using a list or something. But this approach is not very good, but that's the idea of insertion sort. So every time I get to a new item, I'm going to put it into the right place. Now let me show you the slightly weird way of doing this, which is the in-place version. It uses swaps. This is pretty clever. Takes a little bit of thinking to convince yourself this is really the same idea, but it really is. And so the idea is as follows. So I am going to say, for each item, starting from the front, I'm going to designate that item as the traveling item. Okay, so for example, 32 is going to be the original traveler. And then I'm going to step 32 backwards until it's in the right place. Okay, this is getting to the same goal as before. So 32 is going to look backwards and say, is there any way I should be? No. Okay, so what that means is that 32, with regards to the items that we've thought about so far, it's sorted, right? So like if we were to put it in that other array that we imagined in our earlier naive version, it's there. Okay. 15 comes along and 15 says, where should I go? So where should it go? Left. It goes to the left of 32. And at this point, it's done. And we say, this is now sorted. Again, you can think of this as that other array, the gray boxes. But here we're not making another array. Okay, 2 is the new traveler. Where does 2 go? All the way over. And what I'll note is actually I've temporarily broken this invariant that I didn't actually specify out loud, that all the items up to I should be sorted. So that's kind of the way that insertion sort is thinking about. This is, in some sense, a virtual version of that other array that has the items in the right place. Okay, then 2 gets here, and now the invariant is restored. And these are the items in the output sequence. Okay. Questions about that? Okay, 17, where does 17 go? Goes between 15 and 32, 19 moves over, 26 moves over. What does 41 do? Stays, great. Okay, now we got 2 17s left, okay. And again, you can think of these numbers here as the numbers in that output sequence, and there's only 2 items left in the original sequence. Okay, how do I get 17 into its appropriate place? We slide it over, boop, boop. Okay, good. That's insertion sort. Questions about this? Seems like a lot of things to digest. And you do like maybe 20 or 30 minutes of playing around with these in discussion section or after class, and then they sink in. Insertion sort's a little tricky though, I find. Like when I first learned it, I remember being like, I think I got that, but felt like I didn't quite get it. Anyway, but it's pretty. Okay. So to start setting the stage for the analysis we'll do next time, I'll just show you a couple like slightly bigger examples of insertion sort. Let's say we want to sort the letters in the word potato, P-O-T-A-T-O. And so what we're going to do first is P is the traveler. It's the item we're going to shift over, and P doesn't go anywhere, 0 swaps. How about O? When O is the traveler, their active item, will it move? L-M-N-O-P. Yes. Okay, good. Okay, O comes before P. T, does it go anywhere? Nope. Okay, how about A? Where's it going to go? It goes over. A-O-P-T, 3 swaps. T doesn't go anywhere. And then how about O? Where does it go? L-M-N-O-P. Ah, it goes, that's right. Remember, O is less than P. That's good. So it's going to go 3 swaps. Okay. So we can think about the work the algorithm did is O moved over, then A moved over a lot, and then O moved over for a total of 7 swaps. Okay. Another one is, I took this straight out of the Princeton book. It's pretty fun. Sort example. And same exact pattern. We can think of gray as like work we could have hypothetically done, but we didn't need to do. Purple is, well, where the active item ended up, and black is work that we did. Like E was here, and it went over, 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 over. 8 total swaps. Okay. Incidentally, each of these swaps fixes exactly one inversion, which is a really interesting property of insertions. Okay. So 36 total swaps. So the question I'll leave you with to think about here, and I guess I'll give you about 30 seconds to think about it and I'll have a closing thought, which is, what do you think is the runtime of insertion sort looking at this pattern? What will be like, you can think of this as the best case and the worst case if you want lower and upper bounds. So I'll give you guys 30 seconds and I'll give you a thought before launching you into the evening, afternoon. Okay, I'll give you a hint and then I'll release you, which is, what would be the absolute best case? What would be the colors of this diagram? What would it look like? And in the worst case, what would be the absolute worst case for this diagram? How many greens and whites would you get? All right, that's it for today. We'll pick up on Wednesday where we left off. Yes.